Okay, 5.3, some additional properties of the binomial theorem. We're going to take the binomial distribution and we're going to make a graph out of this. So what's going to happen is you're going to place the R values on the horizontal axis. Remember, R stands for the number of successes. So R equals 0 means 0 success. R equals 1 means 1 success. R equals 2 means 2 successes. And you're going to go all the way up until, well, I guess how many trials you've got. So if n is equal to 10 trials, it means you're going to end up with R possible outcomes. Remember, you got to include the 0. The probability of R is going to be the vertical axis, and because this is end up going to be a histogram, you're going to have to take and you're going to add and subtract 0.5 from each of those R's to get the actual numbers on the x-axis or the horizontal axis. I would suggest grabbing out your table. I got these from the back of the book, actually. I didn't run through the formula. I looked for the grouping of 4, and I looked under the column of 0.4, and I got these 5 probabilities. Okay. Now, where those probabilities end up working out to be is they're going to be the height of each of my bars. And where the 0.5 kicks into place is between 0, which would be in the middle of that, 1 would be in the middle, is my 0.5. They bought up in their share, or 1.5, 2.5, 3.5, and 4.5. So those are going to help out with my class widths. And I really want to stress that 0.5 idea because in Chapter 6, that's going to help us a lot with taking this rigid rectangular shape and fitting it underneath a smooth curve and help us find some probabilities. Okay, here we go. We have, only for the binomial theorem, a special way to get up mean. You don't have to go through and take each outcome times its respective probabilities and then add them up. You can just take the number of trials times the probability of success. And to find standard deviation, you're going to take the square root of NPQ. So N again is trials, P is success, Q is now going to be a failure. Don't forget the square root. Okay. Here you got what R, N, P, and Q stand for again, but that should be pretty fresh in your mind. All right. So find the mean and standard deviation of the probability distribution that tosses tossing 4 coins and observing the number of heads occurred. So we're going to run it 4 times at a rate of 0.5. So my mean or my expected value is going to be that rather 4, because of 4 flips, times 0.5. We expect to get 2 heads out of those 4 flips, which makes sense. And the standard deviation is going to be that 4 times 0.5 times an additional 0.5 for the probability of failure. So we're going to end up with half of 2 or the square root of 1, which is going to be 1. So this particular one had a standard deviation of 1. But this only works for binomial types of experiments. So going back to that sharpshooter example from notes yesterday, a sharpshooter takes 8 shots. Her chances of hitting the target are 70%, so 0.7. I'll multiply that out, and I get a 5.6. Now, I know that 5.6 isn't a possible value, but that's okay. That's just kind of an average. So you can expect maybe about 6 hits in that. And to find that standard deviation, you'll take that 5.6, and you're going to multiply it by failure, so the 0.3. So 5.6 times 0.3, and then again, don't forget to take the square root, and you get about 1. I believe it's going to be 30 when you round out. Okay, so that's what you can do if it's a binomial situation. You get that mean and standard deviation. This quota problems is kind of working backwards. I would go ahead and take your book, flip it to the back binomial table that we have on, I believe it's page A10, A11. But quota problems are the minimum number of trials for a given probability. We're gonna solve using binomial probability distribution. We use binomial distributions, kind of work backwards. We're trying to find the minimum number of trials or an n value when we dictate what R is and we dictate what P is. So we know how successful we want to be, and we do know the probability of being successful on one particular trial. We're going to use that table to work our way backwards to find some grouping of n. But we're going to have to use this complement idea because most of the time we're going to have an at least situation. Now, when it's at least, I really don't know when that ends. If it's at least one success, I know that means that successes have to be bigger than or equal to 1, but if we go into 100 trials, I don't want to go probability of getting 1 success, 2 success, 3 success, 4 success, all the way up to 100 and add those up. So a shortcut of that would be to take the complement. So 1 minus the probability of 0. To find 2 successes, so it's going to be 1 minus the probability of 0 and 1. 3 successes, it's going to be 1 minus the probability of 0, 1, and 2. I guess what I'm trying to get at is the pattern is whatever this number is, you're going to subtract that many possibilities up until 1 less than that. So here it was at least 3, so I worked my way to 2. It was at least 2, so I worked my way to 1. It was 1, so I worked my way to 0. So if it was R is at least 99, I would go 1 minus until I got to the probability of 98. Which we won't do that because that is way too many trials. Okay, so here's the scenario. A certain information service is in business of finding addresses of long-lost friends. It claims that to have a 60% success rate. So what that's going to tell me is that the probability of successfully finding a lost friend on each friend is 60% chance. That's going to be the column that I'm looking at in my table. Suppose that you have the names of some friends that you want to look up, the addresses, and decide to use this company to track them down. How many names would you have to submit to be 90% sure that at least 3 friends or 3 addresses are going to be found? Really what we're going to do is we want this R to be greater than equal to 3 to be greater than equal to 0.9 or 90%. Okay, if we're more than 90% successful, that's great. So what I did is I took the complement of that, which would be 1 minus 0 friends found, 1 friend found, 2 friends found, and that's what's going to also drive that being bigger than or equal to 90. I kind of look at it this way, that these 3 have to add up to be 0.1. In order to go 1 minus 0.1 is 0.90. So here's where the table comes into play. And this might work out better when we're actually doing it in person. But now I'm going to look at the table. I'm looking under the column for 0.6. And I'm basically trying to find 3 numbers of 0, R is 0, R is 1, R is equal to 2 that come as close as I can possibly get to 0.9. Okay? And that grouping is n is equal to 7. Because R is equal to 0 works out to be that decimal, R equals 1 is that decimal, R equals 2 is that decimal, and I'm over by a thousandth. I think I should probably be a little bit lower than that. But anyways, that means that I'm going to have 7 friends that I give him the address for to get at least 3 of them found at a 90% rate. Okay, that could be a mouthful. This is definitely something I want to get into the classroom and practice again and again and again, but I wanted you to hear it first. So here we go. Try that out, see how it goes, and we can go from there.